You see all the blue dots there. It's a very cluttered. You can't detect any subsets there. You can't figure out any clusters. So probably, most likely, we are recording from multiple neurons at the same time, but we are unable to do spike sorting. So we have to accept multi-unit activity, take all the activity together. And if we would attempt to do spike sorting, we would get a lot of mistakes. So we didn't do it. We just kept everything together. But we were, of course, curious to find out if there was anything in there. That's slide 73. You see that for different trials, and you build up the histogram, you see that that there is definitely an orientation tuning, as shown in slide 73. You see that the firing rate for after stimulus presentation, that's the vertical red line, for 0 is much higher than, for example, for 45 degrees. So there is definitely a tuning. So the data are usable. And then, you have to come up with some features. Here we look at the histogram that is binned in bins of 25 millisecond. We consider 20 bins. We have 96 electrodes. So this way we get 90-20 features in total. So almost 2,000 features. Okay. We can look at different possibilities here. We can do feature selection, as we said before. We can use a filter for that. So you know what it means. You're a wrapper, and for that we use GMDH, so the one we just have shown as well. Classifier-wise, you can also use different types of classifiers. You can use a linear support vector machine or a linear discriminant analysis classifier. And then you have, of course, a multi-class problem. Remember, you have 8 different orientations plus the background, so 8 plus 1. So multiple classes, and different ways to combine the outcomes of different classifiers. You can do simply a voting scheme, or you can do something that's more sophisticated, as indicated by these the methods in these publications. Looking at slide 76, you see on the left side, if you would pairwise train your classifier, for example, distinguish between 45 and 67 degrees orientation, or between 45 and 128, and so on. You train your classifiers like that. Then you get 36 of those classifiers, if you consider orientations, and you see the plot there. So it is somehow between 90 and 100% accuracy. That's the vertical axis. So these are 2 different curves. The black and the red one are for 2 different types of combinations. And the red curve, the red panel, shows you, as you can expect, the bigger the difference between the 2 orientations to be discerned, the better the accuracy. I mean, that's actually what our gut feeling is telling us as well. Okay, so let's see at the performance. That's slide 76. You can plot some confusion matrices. A confusion matrix is actually plotting probabilities of estimated and true classes. What is interesting, of course, the orthogonal indicated in black. These are the correct stuff, and anything that's deviating from that that the orthogonal is incorrect, and you can have different combinations. You can have a GMDH wrapper that is using an LDA classifier, and the Wu et al. Scheme to handle the multi-classification problem. So there are different possibilities, and slide 78 is sort of summarizing it all. And there you see you have 8 different combinations of classifiers, wrappers, and multi-class resolving multi-class issues. And you see that the best performance is 93%. Obtained by GMDH in combination with LDA and Wu et al. Method number 2. And you see accuracy. You can also see the Brie score, which is also a metric, and the smaller the Brie score, the better. So it's another way of looking. I mean, there are many ways to look at accuracies. So this is one of them. Okay, so this was a bit about the visual stuff. Let's look at motor BCIs again, because motor BCIs are the most prevalent type of invasive brain-computer interfaces. And more recent developments are based neither on spikes, neither on local field potential, but electrocorticography. And we have introduced that before. I'm now on slide 80. Here you see a lab you're collaborating with. You have a lady who's paralyzed, end-stage amyotrophic lateral sclerosis. It's a progressive disease, so she's completely paralyzed. And she has been implanted by a few strips of electrodes, as shown there, and also a strip over the hand part of the motor cortex, so-called hand knob area. And the lady has to imagine closing, if I'm correct, the right hand, and to select a particular character that is displayed on the screen. So on the screen she's looking at is a tablet, and it is indicating row per row, and you select a particular row by imagining a closing a hand, and then pixel per pixel, then character per character, that row is then highlighted, and you confirm your selection by closing the hand. Not an easy task. You see the setup. There is some electronics there. That's the wirings that come out of the brain have to the wirings are under the skin, going towards the chest, where there is a transmitter, and then on the other side, outside the body, there is an antenna that is picking up the signal, and so on, and then that signal is being processed and decoded. On slide 81, you see the implants on the right-hand side. This is an X-ray showing the implants, and the ones that are being focused on is the strips that are implemented over the hand motor cortex. And there were 2 electrodes, E2, E3, that are useful. Not the 4 of them, only 2, and actually it was only 1 that really worked well. That is used to do the decoding job. So in slide 82, there are 2 videos showing how it works. I hope these videos work. I will try to start at the bottom left.
Patients with brainstem strokes or degenerative disorders, such as amyotrophic lateral sclerosis or ALS, can develop locked-in syndrome. They have normal cognition but are unable to move or speak owing to the loss of voluntary muscle control. Patients with locked-in syndrome can sometimes communicate using a letterboard or a camera that tracks eye movements to allow the selection of items on a computer screen, but often can only answer closed-ended questions by blinking their eyes. The ability to communicate has been associated with higher quality of life, but existing systems are very limiting, and certain light conditions make eye tracking difficult. In this brief report, investigators present the case of a 58-year-old woman with late-stage ALS and locked-in syndrome who received a brain implant that allows her to independently communicate using typing software. Subdural electrode strips were placed over the hand region of the left motor cortex to detect the neuroelectrical signals generated when the patient tries to move her right hand. The electrodes are connected to a subcutaneously placed amplifier and transmitter in the left thoracic region that transmits signals wirelessly to a tablet device. The tablet separates activated brain signal from background electrical activity to translate cortical signals into control signals for several computer tasks. The algorithm and parameters of the decoding software were tested and optimized as the patient practiced activating her motor cortex, learning to regulate the magnitude and timing of the brain's signal. The patient performed 44 spelling runs for training and was able to type at the equivalent of 2 letters per minute with nearly 90% accuracy. 7 months after electrode implantation, she used the implanted brain-computer system at home on 32 days and for 86 minutes per day on average. Thus, the implanted brain-computer system shows that autonomous communication is possible for a patient with ALS and the locked-in syndrome. The full report is available at nejm.org.